Let's look at the chemicals in these two containers. Hydrogen peroxide, according to the bottle, says that there should be a 3% solution. However, over time, the hydrogen peroxide slowly breaks down, and that percentage decreases. But it takes a very long time for that to happen. In this package, in this container, if there were any hydrogen peroxide that were produced by respiration, how the plant gets energy from its stored food, that hydrogen peroxide would not break down fast enough in order to become safe. And so that's why the plant has catalase enzyme to break that down faster. However, as we saw, the catalase enzyme that's in the potato is sensitive to temperature. We say that it's thermolabile. It's temperature sensitive. There are other things that are found in plant materials, like vitamin C. Vitamin C is also thermolabile. And in our next project, we'll look to see what happens to the amount of vitamin C as foods are cooked. What does cooking your food do to the nutritional quality of that food? What I want to show you is how we're going to do the measurement of vitamin C. So let's take a look at the practice iodometric titration of vitamin C. The iodometric part means iodine. It gets its name from iodine, which is going to be the titrant that we use in our experiment. So this is very similar to the other titrations that we've done. What you'll need to do is get some of the iodine titrant and put it into a small plastic cup, as we've done before. And then there are two samples that we're going to test. We're going to test a standard and a sample. What the standard has is 100% of the vitamin C at the beginning of whatever it is we're doing to manipulate or change the vitamin C by cooking or by dilution or whatever we're doing. The sample is going to represent what happens after the amount of vitamin C has been reduced by whatever treatment we've given. So there's different amounts of vitamin C in each one. And our goal is to find out what percentage of the standard is the sample. The sample came from the standard. What percentage of the vitamin C that was in the standard remains in the sample? So we're going to titrate both samples. Like we've done before, we'll use a pipette to put 10 milliliters of whichever one you're titrating into a sample cup. Up to the line is only 5 milliliters. So you have to do that 2 times. So once and then again into your cup for titration. And then add, our indicator is starch. So add 1 milliliter of the starch, and then we're going to titrate as we've done before. And what you'll end up with is a blue endpoint. That's what we're looking for, blue color. Now this is how the calculation works. It's not the same calculation that we've done before with stoichiometry. This one is much more direct. So the way it works is we find out how many milliliters of the titrant did it take to titrate all of the vitamin C that was in the standard. We say that that was 100% of the vitamin C that was there before something was done to make the sample, either by cooking or by dilution. The sample has less vitamin C in it, which is why it takes less of the iodine to do the titration. What we want to know is what's the percent of the vitamin C compared to the standard. And so the amount that's in there is proportional to the amount that it took to do the titration. This is the amount that was in the standard. 100% of the vitamin C was in the standard. How much was in the sample is proportional to how much it took to do the titration of the standard compared to the sample. And if you do this math, cross multiply and divide to find the missing part of the proportion, you get 75%. So this sample has only 75% of the vitamin C that the standard had. We'll use a similar strategy to find out what happens to the percent of vitamin C in some material that is cooked or in some other way given heat treatment to see how thermolabile or how temperature sensitive vitamin C is under the conditions that you do for your experiment.